Good morning, fellow mathematicians. I thank you for inviting me to the MCA. My name is Paul Schwahn. I am a PhD student at the University of Stuttgart under Professor Semmelmann. And welcome to my little video talk in addition to my poster. Be sure to check this out as well. First, we are going to talk about Einstein deformations. So, what is the point of this? Suppose we have some Einstein manifold Mg, so some manifold M with a Riemannian metric G that satisfies the Einstein condition, meaning that the Ricci tensor of G is proportional to the metric itself by a constant factor E, which we call the Einstein constant. So one question that arises when we have such an Einstein metric is, are there any other Einstein metrics on M, especially in a small neighborhood of G, or is G isolated in the moduli space of Einstein metrics on M? So suppose this here is the space of all Riemannian metrics on M. So this is, of course, an infinite dimensional space. We have some Einstein metric G. And what has been shown is that if G is not isolated among Einstein metrics, then we have a curve GT so a smooth curve for some parameter T that also consists of Einstein metrics and runs through our metric G. So next question is, how do we find such a curve? So there are some easy ways that are too easy to be interesting. For example, we can define this curve by just taking T times G. So we scale the metric by a constant factor. That's boring. Or we can say we have some curve phi index T of diffeomorphisms from M to itself. Then we can consider the family of metrics where we apply the pullback of phi T to our original metric G. That's also a possibility. So basically we change G by diffeomorphism action. And what we want to do is we want to mod these two operations out in a sense. And what remains is something that we call an essential Einstein deformations. So a curve that is in a sense transversal to both of these actions. So next we consider the problem on an infinitesimal scale. So say we have such a curve of essential Einstein deformations, then we define some tensor H as the derivative with respect to T at 0 of the curve GT. So this is going to be some symmetric 2 tensor. So this is an S for symmetric. And if the aforementioned conditions are true, then H is what we call an infinitesimal Einstein deformation, or short IED. And these IEDs can be characterized by the following set of equations. So first, there is a Laplace type operator, Laplace L, which is called the Lichner-Rohwitz Laplacian on symmetric 2 tensors. And H has to be an eigentensor to this operator to the eigenvalue 2e. Also, the trace of H with respect to the metric G has to vanish. So this amounts to the fact that H is transversal to scaling by constants and also scaling by non-constant functions, because if we multiply a non-constant function with G, then what we obtain is not an Einstein metric. Also, the third condition is that the divergence of H is 0. So this is the divergence operator, it depends on the metric G. This condition basically means that H is transversal to the action of diffeomorphisms. So, what we really want to do in effect is solve an eigenvalue problem for this operator with these constraints. And also, we are in principle interested in smaller eigenvalues of this Laplace operator. So we can ask, what about Laplace h smaller than 2EH? So are there smaller eigenvalues of this operator? Because we can view G, if it's an Einstein metric, as a critical point of the total scalar curvature functional with a certain normalization of volume. And then the behavior of this critical point depends on the spectrum of the linear-Robisch Laplacian on TT tensors. Also TT tensors meaning trace-free and transverse. So trace-free and divergence-free. Also, if we have such an infinitesimal Einstein deformations, there are certain obstructions against integrability. What does that mean? So we cannot expect that any such solution H can be integrated into an actual curve of Einstein metrics. There are certain conditions that have to be met for this to be the case, and one can also investigate those. For details, I refer you to my poster. So let's advance to the next section. Suppose we have some Riemannian symmetric space M equipped with an invariant metric G that is irreducible as a symmetric space and of compact type. So we can write as M as a quotient G over H, where those are compact Lie groups. In particular, this is an Einstein manifold. Okay, we can use this homogeneous structure here to do a bit of analysis. So what we do is we consider this space of symmetric two tensors on M that are trace-free. I denote this with a little 0 here. We can view this as a left regular representation of the group G. So G acts by translations, and we can just translate any such tensor around. And any such representation can be decomposed by the famous Peter-Weil theorem for homogeneous spaces. So first we have to complexify this so that this holds. Then we can decompose this as a direct sum. In fact, we have to take an appropriate closure, but that's topological details that are not very relevant. So the sum runs over all highest weights of representations of G. And we have as summand the representation V gamma, where V gamma is the up to equivalence unique irreducible representation with highest weight gamma. And this occurs with a certain multiplicity, which is counted by this Hom space. This is the space of H invariant homomorphisms from V gamma to the trace-free elements in the second symmetric power of the isotropy representation. So this M, the isotropy representation, is basically the fiber of the tangent bundle of M. And this here is, as I mentioned, the multiplicity of our summand V gamma. And that this is the case follows from Frobenius reciprocity. So why do we do this? Because in our case, conveniently, the operator lambda L acts or coincides with the Casimir operator of G on this left regular representation. And the Casimir operator, in turn, acts as a constant on each of those summands that only depends on gamma. So, in particular, to be precise, what happens is that the Casimir operator of G on a summand of type V gamma. Let's denote this with a little gamma. Is multiplication with a constant that's given by Freudenthal's formula, which is gamma plus 2 delta G, where this is the half sum of positive roots of the Lie algebra G in a product with gamma. And this inner product takes place in the dual space of the torus Lie algebra that we have chosen. That goes without saying, basically. So, these are the eigenvalues of this operator. So the spectrum of this Lichner-Horowitz Laplacian is basically served to us on a plate. Now the more difficult part is to determine which of these summands contain divergence-free elements, because this is the condition that must be met. So we have to do some additional analysis to do that. Okay. I'll give you the upshot of what has happened. Basically, this problem of stability, this eigenvalue problem, has been settled for the irreducible complex geometric spaces, and the bulk of the work was done by Koiso in the 1980s. So he analyzed the stability of compact symmetric spaces based on the known classification. You will find the results in my poster. And he left some cases unfinished, and I contributed to settling this problem. What I did was I proved that the symmetric space, well, Lie group, in fact, SUN, is, at least for n greater or equal to 3, linearly stable. For the definition of these stability terms, I also refer to my poster. And also the complex Grassmannian that's given by SU P plus Q over S of UP times UQ is for P greater or equal Q greater or equal to linearly stable. So what does that mean? Basically, there does not exist any eigenvalue of this Lichner-Horowitz Laplacian that's smaller than 2e on TT tensors, so on trace-free and divergence-free tensors. The next logical thing to do is to turn to general homogeneous spaces that are not necessarily symmetric. And there things don't work out that nicely. Because, okay, let's say we have the following setting. M is some homogeneous space, a quotient of Lie groups, G over H. G is compact, and we have some other assumptions. So we have G is the standard Riemannian metric on M. And then we have, in fact, the following. We have that the Casimir operator of G equals a Laplace type operator. But this is not the Lichner-Horowitz Laplacian in general. So what is this? This is this standard Laplacian. It's defined completely analogously to the Lichner-Horowitz Laplacian, but it's using a different connection. So the Lichner-Horowitz Laplacian comes from the Levi-Civita connection, and this operator here comes from another connection, which is the sometimes called the Ambrose-Singer connection, or the canonical connection of the homogeneous space. So what we have to bear in mind that we have chosen a reductive complement. So say this is the Lie algebra of G, and this is the Lie algebra of H. Then we just simply take the orthogonal complement with respect to the killing form of G to obtain the reductive complement M. And to this reductive complement corresponds the Ambrose-Singer connection, and this gives rise to this Laplace type operator. So, and the difference between those operators, it is not completely unknown, but it depends on the structure of this reductive complement M inside G. Okay, but how can we salvage this? So basically we have to investigate the difference between those two operators. Let me turn to some examples so that you don't get completely bored. First example is the Bézier space. We take the Lie group SO5 and mod out SO3, and in the following way, SO3 is embedded by its action on its 5-dimensional irreducible representation. So this quotient is called the Bézier space. And this is isotropy irreducible, and in particular it's Einstein when equipped with a standard metric. So yeah, what do we do? This space carries a G2 structure, as it turns out. And this G2 structure manifests as a certain 3-form, sigma 3-form on M. And we can express the difference between those two connections in terms of sigma. In fact, we have nabla equals bar nabla plus tau naught over 12 times sigma, where tau naught is some scaling factor. So, okay, so we know what the difference between these two connections is, so we know in principle what the difference between these two operators is. And so what we do is we translate the eigenvalue problem, for the Lichner-Robisch Laplacian on trace-free, divergence-free symmetric 2 tensors into an eigenvalue problem for this other Laplace type operator that is slightly more complicated because we have to analyze several eigenspaces for each eigenspace of this operator on a certain subbundle of 3 forms, so of lambda 3. Okay, so yeah, my supervisor, Professor Semmelmann, and I succeeded in showing that this Bézier space is in fact unstable. So it has a sufficiently small eigenvalue of the Lichner-Robisch Laplacian. Okay, second example. Let me pull that down again. We take our manifold to be any homogeneous nearly scalar manifold of dimension 6. So there is a there's a classification of homogeneous nearly scalar manifold. There are essentially 3 interesting examples. And yeah, what do we have? Say J is our almost complex structure on M. Then we can express the difference between the two connections as follows. Nabla xy equals nabla bar xy plus 1/2 J composed with nabla xj acting on y. So this here is the relevant difference term. And we can do basically same spiel as here. We can translate the eigenvalue problem for the Lichner-Robisch Laplacian on symmetric 2 tensors by some tedious discussion into an eigenvalue problem for this other Laplace operator. And this time turns out that it works nicely on 1-1 forms that are orthogonal to the Kähler form. So primitive. Yeah, and there has been some work already on the stability of these examples. And my work, what I'm currently working on, is to complete the stability analysis of these examples. And also I investigate the integrability of the IEDs in the cases where they exist. So, in the mentioned examples, we utilize the geometric structures of a manifold. Here we have the G2 structure that serves neatly to express a difference term, and here we have the almost complex structure, and in general we have some operator that would depend on the structure constants of a reductive complement M. So, in closing, I'm going to present another example that shows how the structure that's already present on a manifold can help with the stability analysis. So one thing that is possibly a source for an unstable direction is the canonical variation associated to a Riemannian submersion. So say we have some Einstein manifold again, and we have a Riemannian submersion from the total space M to some base manifold B. What we define is the vertical distribution inside the tangent bundle of M. These are basically all the subspaces of the tangent spaces that are tangent to the fiber, so to the pre-images of points in B. And we take the orthogonal complement with respect to the metric G to obtain the horizontal distribution inside the tangent bundle. Now, the canonical variation of G is defined as follows. We define a curve or a family of metrics GT as follows. We take the same metric G on the horizontal distribution, but on the fibers, we scale the metric with a factor T. So the base manifold stays the same size in effect, but the fibers vary in size. So, I already mentioned that if G is an Einstein metric, then it's a critical point of the total scalar curvature functional under suitable volume normalization. So therefore, the T equals to 0 must be a critical point of the scalar curvature along GT. So, it means 0 is a T equals 0 is a critical point of the scalar curvature normalized in the following way. What we define is these is the auxiliary function phi of T. So basically what we take is the scalar curvature of GT. This is going to be constant for every parameter T, even though these metrics are not going to be Einstein in general, but they will all have constant scalar curvature. And then we have some volume factor. So we take the volume of the manifold with GT and divide it by the volume of the manifold with G, and take this to the power of 2 over n. This is our auxiliary function. And yeah, it turns out that our metric G equals G naught is going to be a critical point of that function. So how does that help? The graph of this function can take on multiple shapes. So it can, basically we can discuss the graph and search for critical points of it, or search for regions of monotonicity. And this behavior can be characterized by the dimensions and the scalar curvature of the base and the fiber, respectively. So there's one particular case I want to emphasize. So under certain conditions, say, I call it case 1, never mind that there won't be a case 2 in this talk, but it's just one case that can happen. Say this is our t-axis, and say this is our phi. then it can happen that the graph looks like this. So this is 0. So we have a minimum here. And minimum means that the metric is unstable. If we go along the direction of this curve of metrics, we find an unstable direction for the metric. And we have, so we haven't done any analysis of this Riemannian at all. We have just considered this canonical variation. Also, a nice bonus is there is, in this case, a second critical point at some T1. So we have found a different metric, G T1, that is a critical point of the scalar curvature along this variation. And under some mild assumptions, that I'm not going to discuss right now, G T1 is in fact a critical point of the scalar curvature functional restricted to metrics of fixed volume. So that means equivalently G T1 is Einstein. So what have we done? We have found a second Einstein metric on the manifold M that is distinct from G. So where was this employed? One famous example is the Jensen matrix. Example, Jensen matrix on S 4m plus 3, so the 4m plus 3 dimensional sphere. This can be written as a Riemannian submersion with fiber S3. Yeah, and so I close with that. I thank you all for your attention, and I hope I haven't bored you too much. Thank you.